We've all heard of DI, but do you understand the shocking truth behind why senior engineers obsess over it? Let's dive into the real implementation. We've all heard of DI, but do you understand the shocking truth behind why senior engineers obsess over it? Let's dive into the real implementation. Okay, let's be honest. Dependency injection, or DI, is one of those concepts that seems to exist in a frustrating twilight zone. You're told it's essential for maintainable, testable code. You read articles, watch tutorials, and you think you get it. Then you try to apply it, and suddenly you're tangled in a mess of abstract classes, interfaces, and factories. You start wondering if it's just a buzzword. But it's not. The core principle is genuinely powerful. The problem is, most tutorials only scratch the surface. They show you the basic constructor injection, passing dependencies directly into a class's constructor. That's the training wheels version. What they don't show you is the deeper, more complex, and frankly, more elegant ways senior engineers are actually using DI. And that's what we're going to cover today. We're going beyond the textbook examples. Let's start with the foundations. The first real wave of DI popularity coincided with the rise of the Spring framework, released by VMware in 2003. Before Spring, enterprise Java development was a tangled web of tightly coupled components. Think servlets directly interacting with JNDI for database connections, business logic classes importing dozens of other classes. It was a maintenance nightmare. Spring's DI container provided a much-needed solution, allowing developers to define dependencies externally and let the framework handle the creation and wiring of objects. And while the basic concepts remain similar, the way we implement DI has evolved considerably. The initial Spring versions primarily focused on XML configuration. Imagine meticulously defining every bean, every dependency, in a massive XML file. It worked, but it wasn't pretty. By Spring 4, annotations like it auto-wired became dominant, offering a more concise and readable approach. This was a significant improvement, but it still felt limited. It hides the complexity, sure, but it doesn't truly teach why you're doing it. Here's your first revelation. The real power of DI isn't just about passing dependencies in. It's about creating abstracted relationships between components. It's about decoupling. Let's look at a simple example. Imagine you're building an e-commerce platform. You have a product service that needs to send emails to customers. The naive approach would be to have product service directly instantiate an email service. Product service is now tightly coupled to email service. What if you want to switch to a different email provider, say, from SendGrid to Amazon SES? You have to modify the product service code directly. Now, with DI, you define an email service interface. Both SendGrid and Amazon SES would implement that interface. Product service would then depend on the interface, not the concrete implementation. You can swap out the email provider without touching the product service itself. Simple enough, right? But that's not the strangest part. The really clever stuff happens when you start thinking about how those dependencies are provided. Most tutorials stop at constructor injection, passing the email service implementation into the product service constructor. That's good, but it's not enough to unlock the full potential. Let's introduce a deeper layer. Consider the concept of scope dependencies. Think about a social media platform like TikTok. They have millions of users, and each user has a unique profile. The data associated with a user's profile, their followers, their likes, their videos, needs to be managed efficiently. TikTok wouldn't instantiate a whole new user profile object for every request. That would be catastrophic. Instead, they likely use a scope dependency, such as a request scope. This means that the user profile object is created once per HTTP request, associated with the specific user making the request, and then destroyed when the request is complete. The dependency injection container manages this lifecycle, ensuring that each user sees their own data. This goes beyond simple object creation. It's about managing the state of your application. It's about optimizing performance. And crucially, it allows you to write testable code because you can easily mock out different scope dependencies for testing purposes. Imagine being able to inject a mock user profile that returns predefined data, perfect for unit testing. But that's not the strangest part. Let's talk about dynamic dependency resolution. This is where things get really interesting. Most DI frameworks allow you to configure dependencies statically, meaning the mapping between interfaces and implementations is defined at application startup. But what if you need to change that mapping at runtime? Consider a financial application like Bloomberg Terminal. They often need to adapt to different market conditions, regulatory changes, or even failures of external systems. Imagine a scenario where their pricing algorithm needs to switch to a backup algorithm mid-trade due to a detected anomaly. Hard-coding that logic into the application would be a disaster. Dynamic dependency resolution allows you to define rules that determine which implementation to use based on runtime conditions. This could be based on environment variables, configuration files, or even the results of complex calculations. The DI container then dynamically resolves the dependency based on these rules. Essentially, the application itself can configure its own dependencies. This technique is often used in conjunction with something called feature flags. A feature flag is a simple Boolean value that controls whether a particular feature is enabled or disabled. You can use feature flags to dynamically switch between different implementations of a dependency, effectively A/I/B testing different features or rolling out changes incrementally. This level of flexibility is crucial for applications that operate in highly dynamic environments. It's about building systems that are resilient, adaptable, and continuously evolving. Now for the twist nobody expects. The current trend in cloud-native development, serverless functions, and microservices, is actually pushing DI beyond traditional container-based frameworks. Think about AWS Lambda. Each Lambda function is a self-contained unit of code that is executed in response to an event. They don't have access to a global DI container like Spring. So, how do you achieve DI in a serverless environment? The answer lies in dependency injection libraries specifically designed for serverless functions. These libraries typically inject dependencies directly into the function handler, often using a technique called constructor injection, similar to the basic example we covered initially, but with a focus on lightweight, runtime-based injection. They can also integrate with external configuration services to dynamically resolve dependencies based on the environment in which the function is deployed. The core principles remain the same: decoupling, abstraction, testability, but the implementation is tailored to the constraints and characteristics of the serverless paradigm. This highlights that DI isn't just a framework-specific technique. It's a design principle that can be applied across a wide range of architectures. It's about embracing abstraction and decoupling, regardless of the technology stack. Finally, let's conclude. Dependency injection isn't just about passing objects into constructors. It's a powerful tool for building robust, maintainable, and adaptable software. It's about designing systems where components are loosely coupled, where dependencies are managed externally, and where the application